Hello everyone, my name is Rong Gu. I'm from Mälardalen University in Sweden and I'm now a postdoc researcher. I'm happy to have this opportunity to introduce my research about integrating the power of machine learning and model checking in safety critical systems. First, I would like to thank the organization of LiVe24, especially Yan, who allows me to give the presentation in this way. Happy to meet you all in person, but I happen to have a very important thing to do today in Sweden, so I couldn't join you this year. But I want to say machine learning and model checking is my main research passion. So if you are interested in any of the topic that I'm going to introduce in the following presentation, please don't hesitate to contact me and we can talk about it later. So my research can be roughly divided into 4 directions, but today I'm going to only talk about controller synthesis for autonomous systems, because this is where I combine machine learning and model checking the most. Well, when we talk about system design, we often think of 3 steps: requirement elicitation and analysis, system design and implementation, and testing. This is quite natural for all of us, right? But for system synthesis, however, it's a little bit different. It starts from the modeling of the atomic behavior of the system, not the entire behavior of the system, and then formalize the requirement into a format or a manner that is accurate and understandable by machines. Next, the models and the formalized requirements are fed into the automatic process which compose and sort the behavior of the model in a way that the composed behavior satisfies the requirement. The product of synthesis is a controller of the system, and it is guaranteed to be correct. Or to put it into another words, it is correct by construction. So the keywords for synthesis is automatic and correct by construction. If the last slide is a little bit too abstract, let me introduce it by looking at this concrete example. So this is the query that is provided by our industrial partner, Volvo Construction Equipment in Sweden. In this query, we have machines working together to carry and crush stones. Let's assume that we have 2 kinds of autonomous vehicles. One is the autonomous trucks, one is the autonomous wheel loaders. These autonomous vehicles need to cooperate to load the stones and carry them to different crushers and avoid all sorts of obstacles. They need to go to the charging stations every now and then to ensure their battery is enough to finish their jobs. So to realize such an autonomous query, there's a lot of challenges. But today in this presentation, let's only focus on mission planning for the autonomous vehicles. Here, mission planning means to find collision-free paths to each of the target positions and schedule the tasks, like digging stones, loading and unloading, etc. So there are many challenges for this so-called multi-agent planning, but now let's focus on 4 prominent ones. The first one, uncertainties. Because the environment is uncertain, like the weather, the road condition, the planning must consider all the uncertainties such that it is robust, right? And we have varieties of constraints. Some of the constraints are temporal. A must be done before B is finished, so on and so forth. And we have collaborations, and we have individual jobs, a lot of things to be satisfied. We have complexity, basically the nature of the problem planning is NP hard, right? So the complexity of the problem increases when the numbers, for example, of the vehicles increases also. And because of the complexity, the resulting plan can be very large, which takes a large memory space. But for embedded systems, the memory space is very limited. How can we solve it, right? So in a nutshell, we want the result mission plan to be safe and efficient. But actually, the most safe mission plan is to let the machines stand still. but it is inefficient. The efficiency is 0 now. So we want to make a balance between safety and efficiency, right? This is our goal. So the first solution that one can think of is reinforcement learning, maybe because it is popular and hot today. Reinforcement learning basically let the machine move freely in the environment and learn the rewards of the doing actions at different states from the environment, and then finally synthesize a controller, which is actually a function that takes into the machine's states and outputs the action with the highest reward. So if we explain the mechanism of reinforcement learning briefly in this sketch, we assume that the autonomous wheel loader starts from the top left corner and aims to go to position A and position B to do tasks. Eventually, it needs to reach the destination here. So to make the presentation simpler, I discretize the environment. But reinforcement learning doesn't need to do that. It can take in continuous states and continuous actions. Now in the beginning, the vehicle has 3 steps or 3 actions to choose from. Go to the left, go to the right, or go down. Let's assume it chooses to go down 1 step. So now the environment tells the vehicle the new state, like the new position, the new velocity, etc., and also the reward the vehicle obtains by moving 1 step down. Now the vehicle has 4 actions to choose from. We assume that it chooses to go to the right, and so on and so forth. When the vehicle reaches position A, it needs to decide whether to move on or stop and finish the task here. Probably doing the task would be a better solution, but it doesn't know. It just tries freely. The environment again would give the vehicle different rewards on different actions now. So on and so forth. When 1 episode of learning finishes, we get a trace. The trace includes the state and action pairs. These pairs are then fed into a formula to calculate the scores of the state and action pairs. Let's say we use Q-learning. This is a classic reinforcement learning algorithm. The formula is called Bellman equation. It takes into account the immediate reward and future Q values. So when the Q values calculated by the Bellman equation converge to the optimal, the learning finishes. Right? Next, eventually the vehicle knows what to do at each of the states. It just looks at the table and chooses the action with the highest reward. Now the problem is, is the learning result correct? Well, we don't know. If we actually look broadly and ask, can we trust the AI in our society, especially when they are used in safety-critical systems? Can we trust them? Well, researchers say no. In this paper article, Adversarial Attack, the authors show that when adding illumination to a picture of a stop sign on the left, a neural network that could successfully recognize the original picture now sees the illuminated picture as a speed limit sign. So this is very dangerous, of course, to make such mistakes in real life, isn't it? And what about the practitioners? I met Thierry, the R&D director of Clearcy, a French railway company. I met him in Dextro seminar, and his talk gives me their engineer's perspective about AI. So I just quote his words and slides here. So from the engineer's perspective, safety equals to sophistication. They just want their products to pass certain laws, standards to pass the certification. But AI is not recommended in any of the standards. What is recommended? Formal methods. In some of the standards, formal methods are actually mandatory. So what are formal methods? Well, they are techniques based on mathematics. I guess I don't need to waste time on this slide because all of you are very familiar with formal methods. So maybe one more thing that I can mention here is that by using formal methods, we can get close to the popular concept of trustworthy AI. and I'll show you how a little bit, the work that we have done. So in my research, I use UPO a lot. UPO is a very successful model checker with a beautiful GUI and powerful engines for model checking, for simulation, statistical model checking, and nowadays it even supports machine learning too. Again, I think most of you have heard of this tool already, so I won't spend much time on the slides too. But like I said, UPO now supports reinforcement learning. Basically, what we need to do here is to build a model just like what we did in the classic UPO, build the time-to-matter model, except now we differentiate the edges with controllable actions and uncontrollable actions. For example, on the right-hand side, we have the model of the, on the left-hand side, we have the model of the vehicle's behaviors, like the acceleration, deceleration. They are solid arrows, which represent the controllable actions that are performed by the system. On the right-hand side, we have the a model of the environment's behaviors, which are modeled as dashed line arrows. They are uncontrollable actions. So we call this new model timed games. And our goal now is to win the game. How to win the game? We synthesize a controller that controls the controllable actions and satisfies the requirement, regardless of how the uncontrollable actions are performed by the environment. So now let's recall what we need to do in controller synthesis. We need to construct the model of the system, and we need to construct the model of the environment too. Now we need to formalize the requirement. In UPO, we use timed computation tree logic, and for example, the first property is called invariance. It means that for all the states in all the paths, the population is satisfied. Now the population is s.p intersects with O equals to empty. It means that the position of the autonomous vehicle, s.p, never overlaps with the position of the obstacles, the capital O. And this property must be satisfied at all the states in all the paths. So this is invariance. Similarly, we can compose the properties for the reachability requirement and the liveness requirement, but I'm not going to show you them all here. Now we have the formal properties and the models. All we need to do is to explore the state space of the model and find out the traces that satisfy our requirement. However, we have another obstacle to overcome because now we have continuous variables here in this model. They are called clocks in UPO and they represent time. So time has infinite possible values, right? It's uncountable and infinite. We couldn't actually have this beautiful, discretized state space if we have time. But UPO uses zones to symbolically represent the possible values of time. And zones are finite and countable. So now we can actually exhaustively explore the symbolic state space, and then based on that, we synthesize the controllers. This is the so-called exhaustive search-based method. Briefly, we search the space of the model and find the combinations of controllable actions. And since now the state space is symbolic, we can exhaustively search it and find out the traces that satisfy the formalized requirement. So now the resulting controller is guaranteed to be correct. This is the formalized requirement. According to this idea, we developed a tool called TAMA, time-to-matter-based mission planning for autonomous agents. In this tool, we have a GUI called MMT, Mission Management Tool, like this. I'm going to show you a video later, so you don't need to look at the picture now. And at the back end, we use UPO to, run the verification, get the witness trace, and then we get a plan based on the trace that we get from UPO. This is what we do in TAMA. And one more thing to mention is that at step 3, all the modeling, the model construction is automatically done by our program. So there's only one thing for the users to do is to configure the environment and click the button. I'm going to show you here in this video. I'm using this Google map and I confine the navigation area. Now I'm adding some obstacles, right, in different shapes. I can even configure the existing time if the obstacles are temporary. And then I'm adding a vehicle into the, several vehicles actually. And also I'm adding these pinpoints. They are the target positions where the vehicle needs to do, to go and finish tasks. And now I'm just, configuring the conditions, like the preconditions, post conditions, the execution time of the tasks, and so on and so forth. So yeah, I open one existing mission, and yes, what I did is to click the button, and then on the back end that I just quickly showed you, I run everything in the server, and the server sends back the result. It's just a 1 second thing. We have the path, we have the mission plan and everything, and the most important thing is that the plan now is guaranteed to be correct. So although everything seems beautiful and automatic and correct guaranteed, but the method now suffers from the state space explosion problem because of the model tracking that we use. So the complexity of mission planning problem increases exponentially when the numbers of the vehicles increases linearly actually. So like in this table, we show that if the number of vehicles is 6, UPO runs out of memory. We couldn't get any result. This is bad. So now we have a dilemma. On one hand, we have the search-based method. It is safety guaranteed, but state space explosion. On another hand, we have the learning method. It is scalable and everything is also automatic, but it's unreliable. What do we do? We want to combine them all to borrow the power of both of the algorithms. This is what we do. We have MCRL, model tracking plus reinforcement learning. And basically, we just build up the model in UPO, but the learning algorithm now is implemented in the external library. So when the model tracking is running, or when the learning is running, UPO calls the external library to call the learning algorithm, right? And actually UPO runs a Monte Carlo simulation first to sample traces from the state space, and then feeds these traces into the external library where we have the learning algorithm. And the algorithm only sees the controllable actions now. And next, we verify the synthesized controller against a liveness property, because we want to see if the vehicle can always eventually reach the destination without collision, no matter how the environment reacts, right? And now let's see the performance of MCRL. So in this table, MC stands for model checking, and MC plus learning stands for MCRL. And like I said, by pure model checking, we stop at 6 agents, 6 vehicles. That's the limit. But if we have MC plus learning, what do we get? We only need 8 minutes to get the result, even if the vehicles are 6. And even if the vehicles are 10, which is the requirement from our industrial partner, we only need half an hour to get the result. And everything is also correct, correctness guaranteed. Since everything is done in the query, everything is done after 1 day of work, so it's offline. Half an hour of synthesis computation time for synthesis is totally fine for the industrial partner. Well, there's another problem of reinforcement learning that we are facing. When we run the Monte Carlo simulation and do the learning, we got a lot of useless information. For example, if I want to try to find a path in this environment, reinforcement learning tends to explore all the environment. And at the end of the day, we only care about one path, that is, reaching the destination. And this is the only useful information that we need. However, all the random exploration is stored as the result of reinforcement learning. So what do? We need to get rid of this useless information and still preserve the correctness of the result. We can still do that by using MCRL. Essentially, we do the liveness verification, and we label the state and action pairs that are visited by the checker. If the liveness property is satisfied, all the branches of the tree-structured state space must be explored. So now we can remove the unlabeled state and action pairs because they don't contribute anything to the satisfaction of the liveness property. They are useless in this sense. So they can be removed, and now the state space, the memory space taken by the strategy, the controller, is much reduced, like what we show here in this picture. The reduced percentage can be up to 99.95, which is extremely high, right? So now we have the method combining model checking and reinforcement learning, and the performance looks good. We can even compress the strategy, but can we do it better? Well, we have two versions of MCRL, and both of them separate the learning and model checking into two different phases. Can we put them together more closely and more smartly? This is the question. So far, we only care about the safety and functional correctness of the controller. However, cybersecurity is also very important for modern vehicles. In 2015, a Jeep is hacked on the highway in the US, and the car's engine is remotely shut down by the hacker. So the driver had to drive into the side of the road to make it stop. It's very scary, isn't it? So to illustrate security, we give you this example. In this map, we have two robots. They are working together to finish a mission. A mission consists of two tasks, task T1 and task T2. An intruder is trying to steal the information from the robots. Assume that the intruder is only interested in the task execution order of the robots. But what he can only see the moving trajectories. In other words, the intruder couldn't see what the robots are doing in each of the cells directly. However, if the robots are careless, they may reveal the confidential information of task execution order to the intruder by only the moving trajectories. Let's see how. So let's see if the robot R1, starting from the bottom left corner, it moves as trace A shows. First 2, 3, and then 3, 3, and then 3, 2, and then 3, 1, and then M, which is the ending point. What happens? From the intruder's perspective, there are two possible task execution orders under this moving trajectory of trace A. In both of these possible traces, the only chance for R1 to do task T2 is at 3, 3, which is before T1. So in this sense, trace A is not secure, right? Because the intruder can deduce the task execution order by only looking at the trajectories of the robot. However, now trace B is secure, because in this trace, robot R can do T1 first or T2 first under the trajectory, right? So the intruder couldn't figure out the task execution order by looking at trace B, which makes the trace secure. Now our target is to synthesize a functional, safe, and secure controller for CPS, cyber-physical systems. In other words, we want to find the controllable actions that avoid dangerous states, reach the goal states, no matter how the uncontrollable actions are taking place. Also, if we have intruders, we want the confidential information to be opaque, so to speak, to the possible intruders. We call our method guess and then check, and we believe it is scalable, sound, and complete. This is ongoing work joint with my colleagues at MDU. And we are going to present our work in this year's fall in the Netherlands. So welcome to the conference and listen to our talk in July. So intuitively, we call our method guess and check because in the first step, we make a guess by randomly exploring the state space and collecting actions that might satisfy the rich and void property. Next, we check the guessed controller against the safety property again. Now the exploration on the uncontrollable actions is exhaustive, so we won't miss any situation that is, dangerous, that may cause a collision at step 2. After step 1 and step 2, there are some iteration, I will introduce later, but next, if there exists a qualified controller, we must be able to find it. This is the so-called soundness. And if the controller is safe and correct, we must be able to find it. If there exists a qualified controller, we must be able to find it. This is called completeness. And once we find the controller, it is guaranteed to be safe and correct. This is called soundness. And finally, we check the safe and correct controller for security. The traces that may leak information, the confidential information to intruders, will be removed from the controller. Now let's go into the details very quickly. So in step 1, we explore the state space by following 2 rules. First, exhaustive exploration on controllable actions, and second, random or selective exploration on the uncontrollable ones. The exhaustive exploration on the controllable actions is to make sure that we don't miss any valid traces. However, to eliminate the state space explosion problem, we only selectively explore the uncontrollable actions at this phase. So at the end of the step, we reduce the state space by only keeping the traces that has the possibility to reach the goal state. However, now, since the environment can choose a different action than what we choose in this step, the guessed controller only possibly satisfies the rich and void property, but not definitely. So, in the next step, we need to check it. But before we do that, let's see why this guess step is important and why it is beneficial. So if we use learning in this step, we can get a very good result. Say in the beginning, the model has 3 controllable actions. We need to explore all of them, right? Assume that we go to left one first. Next, we randomly choose an uncontrollable action to do and moving forward, right? Just by randomly choose one. And then we explore, here at the gray state, we have only controllable actions. So we need to exhaustively explore all of them again, right? And so on and so forth. And in the second branch, we explore this controllable action and then do the random simulation again to choose the uncontrollable actions. But nothing can be borrowed from the experience of the exploration of the first branch, which is a shame. So now if we use learning for different purpose, we use learning to know which uncontrollable ones, actions can finish the exploration as soon as possible. In other words, now we want the environment to win the game in this step because we want to get rid of the traces that are doomed to fail rather than exploring them and cutting them later. It just wastes the computation power. So now we use learning for different purpose. We want to finish the exploration as soon as possible in the first step, right? Now we get a controller, a guessed controller. So in the second step, we update the rules. Now we selectively explore the controllable actions and exhaustively explore the uncontrollable actions. If we call the guessed controller an optimistic controller, then the exploration of the state space under control of this controller means we only need to choose the actions that are allowed by the controller now. So the state space is much reduced, right? But when we meet uncontrollable ones in this step, we need to exhaustively explore all of them because we may miss critical situations in the first step. So now we want to make the complementary action to explore all the possible uncontrollable actions. But now, since the state space is much reduced by the controllers already, the exhaustive exploration on the uncontrollable actions is not a big problem. So after step 1 and step 2, we get a safe and functionally correct controller. Now we come to step 3, but due to the time limit, we only have time to look at line 4 of this pseudocode. So we have two properties, PS and PC. PS stands for secret property and PC stands for the public property. If T1 satisfies PS, which means this trace carries the confidential information, there must be another trace T2 that satisfies PC, meaning that it carries the public information, and the distance between the T1 and T2 is smaller than a threshold, tau. The capital D here denotes the function for calculating the distance between two traces. So if the state space is discrete, actually D can be replaced by equality. Any trace that doesn't satisfy this property will be pruned from the controller. So in the end, the resulting controller is functional and safe and secure. We implement the algorithm in Rebecca, which is a model checker based on reactive objects language. We also conduct an experiment in which we show the numbers of the states explored at each of the phases are much smaller than the pure exhaustive search-based methods. So yeah, this is all for my presentation. Thank you for listening. And again, thank you for allowing me to give you this presentation in the video. And if you have any questions or you are interested in any of the topics, please drop me an email or go to my homepage to look for more details. Thank you very much.